Hey e-skate builders and Raptor riders. In this video we're going to talk about the exciting new developments that has been going on in Immersion Lab. We've got these here, the FOCBOX Unity. What makes this so good is it's smaller, it's more affordable, and it's got higher current throughput than anything on the market. It's going to make building electric skateboards so much easier. It's got a switch in there so you can turn it on and off, all in one tiny little package, and the tests so far are super impressive. I've actually got Jeff here today with me. He's come all the way from the States to show me this and demo it, and we're going to sit down now and we're going to get in depth and talk to Jeff, the engineer behind the FOCBOX Unity, and find out why he made it. Let's do it. Okay, I'm sitting here with Jeff. Jeff, just quickly introduce yourself so everyone knows who you are and what you do.
Yeah, sure. I'm Jeff. I'm finishing up my PhD right now at UC San Diego. I'm a longtime user of brushless motors and motor drivers, and I kind of just got involved with this project after looking at the FOCBOX because it's such a competitive offering in the market, and realizing that I could maybe even improve on what it was doing there.
So Jeff, just before we get into the nitty gritty stuff, can you just tell me what it is you do? Who are you? What sort of person got you here today? Like, what is your background? What did you study? Why the hell are you making high performance, super compact, awesome motor controllers? I'm getting my PhD right now in control systems engineering, more specifically robotics. I have a pretty strong background in motor control and design because obviously we use them all the time in our robot prototypes in my lab. And I initially got started on the whole thing just looking at the FOCBOX and looking at what a competitive offering it was to use. This is the FOCBOX for anyone who doesn't know.
To use just actually as a motor controller within a robot. And I started looking more in depth into it. And I realized that the hardware might be something that I could contribute to and improve upon. So I kind of dove in off of that, and 8 months later.
Yeah, wow, 8 months. So tell me a little bit more about this. So is this what you thought it would be when you started, or did it sort of end up different in any way? Like what sort of things happened through the development that you didn't expect to realize, and are you happy with what you actually ended up with here?
Yeah, it's definitely evolved over time. So when I first started the project, really the initial focus was just looking at why was this motor controller so expensive, really? And my first initial driving thing was all focused on cost and bringing down the cost to make it easier to get your motor controller. I couldn't understand why my motors only cost, $50 to $100 a piece, and my motor driver was comparable cost. It seemed kind of crazy to me. So I started looking through the BOM, and I was like, wow, I can fix this. This is something I can fix. And so I started in on that, and that was kind of my first thing I was thinking about. But as I went, I kind of started to realize the motor controller didn't actually include everything you needed all the time, and so there was some...
Like the switch, right?
Yeah.
This is obviously a switch, but it needs circuitry, right, for it to function.
Right, exactly. And so I found it kind of weird that everyone was having to buy these separate E-switches, and they were getting... It's only a couple dollars in components to build one of the electric switches, but in order to sell it standalone, you have to sell it for $30-$40. And so, I didn't like to see that these e-skate builders were getting nickeled and dimed on that. And so,
exactly, and this is an example of what Jeff's talking about here. These are two separate motor controllers, but there's also another little circuit that we had to put outside of those just so you can turn it on and off. And what Jeff has been able to do here is actually put all of those into one board, and it's smaller. Yeah. Which is really impressive.
Yeah, so that was kind of where I started. And then sometime around when I got one of my earlier prototypes working, I got in touch with Immersion and saw if this would be something they'd be interested in working with me on. And that's, I think, when the project really took off and became something entirely different, because they just have so much experience in the e-skate market and what e-skate builders want, what they need. And through their experience and my ability to implement some of their ideas, I think we've really created something unique here that
yeah, I mean, some of the things that I really just love about this is it's actually going to be cheaper to make.
Yeah.
Which for business is great. You know, if we can bring the cost of technology down lower so more people can afford this sort of stuff, so they can build really high performance electric skateboards. One of the challenges is trying to make things cheaper but also keep performance equal or better. And in this case, you've actually been able to make this not only cheaper, but it actually can handle higher current.
Yep.
It's outperforming the more expensive version. So how do you explain that? I mean, what is the keys to making that happen?
Yeah, so I think one thing that we're doing differently here from the existing designs is we've gone with a single-sided layout, which was pretty labor intensive from a design standpoint. It required a lot of puzzling together. I don't know if you can see this up there, but it's extremely densely packed layout. So it was some man hours, but ultimately, because of that, we get a nice flat surface on the bottom of the PCB, so we can get a huge thermal pad on there and really suck the heat out of the board before it melts anything.
Whole bottom, basically, where is it? Like this whole strip here is literally contacting the aluminium, right? This whole section here, and that's where all of the MOSFETs are. And that's what generates the heat, doesn't it?
Right, yeah, that's where the bulk of the heat is coming, just from the FETs during high current pull.
Yeah. So with this design, because there's no other components, and you can't see that because it's screwed on here, but on the bottom of this circuit board, it's just flat. There's no little components, there's nothing at all.
Right, yeah, it's completely empty. And it also makes manufacturing cheaper and easier, because for those that know about PC manufacturing, you actually have to reflow each side, and
so that way.
So when they flip it upside down, if they have to do that, then they actually have to individually glue each of the other components that were on the flip side, so they don't melt and fall off when you reflow the top of the board. So it adds extra steps to manufacturing. It becomes harder to check reliability when you run through and do optical inspection on all the components. And so overall, it's simpler. It's more difficult from a design standpoint, but it's simpler once the design is finished, right? So it's worth the upfront effort.
And one of the cool things about this, joining two motor controllers that traditionally are separate items, joined together with wires and separate like power connectors here. You can see this one, I'll just disconnect it, but there's actually two of things that you don't necessarily need to have there, because here there's one only, and it just makes sense. Like, why have extra components duplicating things if you don't need to? It only adds to the cost and you don't get any other benefit.
Yeah, and there is a lot of things that end up getting duplicated in these kind of designs. Connectors, that's extra cost. The 5-volt regulation for the microcontroller, extra cost. The microcontroller itself, extra cost.
Like just the plastic cover,
the cases, the milled aluminum pieces. It all adds up, and we can pass some of that savings on to the customer, which is awesome.
And one of the things that people might not fully understand, but to make two motor controllers work together, they need to be connected anyway. You can see here, these guys are connected with these two little wires. Do you think that actually opens the door for reliability issues and stuff like that? I know we have to glue these connectors on because it's high vibration environment. Going to something like this, you don't have these extra wires that can get damaged or come loose. It's all communication is happening through the board itself.
Yeah, exactly. And ultimately it's simpler from a reliability standpoint in that, like, you're only relying on a single code base, single microcontroller. Every time you update, it's just on the one microcontroller. When you change settings, you know you're sending them to both your motors. So there's less concerns there of accidentally assigning settings to the wrong microcontroller, for instance. Everything is more organized. It's much easier because from the start, the thing was designed for your dual drive electric skateboard. It was designed with that purpose in mind rather than as kind of an afterthought wiring together.
I think that's sort of like an ad hoc way of doing it in a way. I mean, some people might say, oh, look, it's better to have modularity, or it's better because if one fails, you can just swap one. But I think when you weigh up all the pros and cons and start to see that you also, you're getting a more compact thing that's easy to use and it's cheaper, I guess the only question left is about reliability. People are going to continue to say, well, I prefer to replace just one instead of a whole one. But I think that reliability is actually going to be higher with this, just because the fact that you can dissipate the heat quicker, it can handle higher current naturally. Do you think that's going to make a difference in terms of longevity for the board?
Yeah, we've definitely, because of the fact that, one failure could bring down both your motor controllers, we've really put a focus on designing this to be robust. And one thing that's been awesome working with Inertian has been, I've been able to communicate and talk about a lot of the failure modes that they've identified through their warranty service. They're getting a ton of these motor controllers back on a regular basis. And so we can look at it and say, hey, what has been breaking on these motor controllers and how can we address those problems?
Some people are able to destroy their whole motor controller just by disconnecting this cable at the wrong time, right?
Yep, exactly. It's crazy. And so first of all, that problem's eliminated. Additionally, we've actually added full protection circuitry to all the Hall sensor input ports. So obviously you have all these delicate sensor wires running right alongside your motor phase windings, and they're going into your motor. So sometimes on lower quality motors, people have had problems where the phase wires or the Hall sensor wires actually short out to the phase wires. And what that does is it's gonna send full motor voltage back into your microcontroller, which will instantly blow it up.
Yeah.
And that basically just nukes your board. So by adding full protection circuitry there, we can guarantee we can put full motor voltage back into this Hall sensor port, and the only thing that's going to happen is your Hall sensor is going to quit working, and the motor controller will automatically just switch into sensorless mode and keep spinning your motors, and you'll be able to ride it home and hopefully identify the issue and fix it.
Cool. So it's probably harder to break.
Yeah.
With these changes.
Mm-hmm. Yeah, and the thermals are better. We have really good capacitance, and because of the way this board is laid out, the bulk capacitors for both motor controllers can kind of help each other out when they're working together like this.
Yeah, okay. Yeah, so you get the benefit of having them all on the same board together.
Yeah, exactly.
Cool. Now, one of the things that I've always found really, it's sort of like a pain in the ass. Basically, when you set up your motor controllers, yes, you've got to make sure they're connected with these wires and physically everything's got to be right. But one of the other things that always was annoying with these is you have to run motor detections once on this side, and then you basically have to do the exact same thing on the other side to get your skateboard working. Mm-hmm. Now, what is the difference between this one? You've been able to make that one process.
Yeah, so we've really tried to rethink the calibration process and turn it into less of a pain point essentially for the user. Our theory is that people really don't enjoy motor calibration. I don't think that's the fun part of building your electric skateboard.
And in mass production as well, our team, our production line, hate it as well because it adds 5 minutes to every single build because they've got to run it twice. It's just a waste of time.
Yeah.
So how is this different?
Yeah, so we actually have put a huge focus on kind of improving the motor calibration routine, automating it, and just making it, essentially nearly a one-button process where you click, you run the calibration, all the parameters are auto-detected just like they were before, but rather than clicking all these different buttons to making sure all the settings are going where they need to, we're going to take care of that for you in software, so you don't even have to think about it. And then additionally, we've worked on, a couple new algorithms for one pain point that I identified personally was the Flux linkage calibration. When I'm looking on the eSkate forum, for instance, I see a lot of people having trouble with trying to get their motor to pass that test because it's a little bit of a chicken and the egg problem. You need to spin up the motor to test the parameter to figure out what the parameter is of the spinning motor. But so you have to know something before you know it.
Yeah.
And so what the current FOCBOX does is it it just kind of guesses random parameters until it sees that the motor starts spinning. But a lot of the time, that never happens. If you have a weird enough motor, the parameters that it's guessing aren't ever right enough to get the motor spinning correctly. And so it just was kind of a pain point, and you had to try a bunch of different settings, and it was a trial and error process.
Yeah.
You're wrestling with the software, and if you don't fully understand what you're doing, it's really difficult.
I know sometimes I've tried to do motor detections and it won't work, and it won't work, and it won't work, and then it will work magically. It's
nothing's
just
changed.
Random. Yeah, nothing changed.
Yeah, so instead we developed kind of, we looked at some existing algorithms that were out there, and we found one that's interesting. Rather than actually spinning up the motor, you can just hand spin the motor. So you hand spin the motor, you monitor the back EMF, integrate it through time, and you can find the exact same parameter, the flux linkage parameter, just as accurately, if not more accurately, with that method. And so we implemented that in software, and that'll all be open source. So, if anyone wants to go back and implement it on the old motor controller, that can be done too.
Cool. And one of the things that I think is really cool about that feature, that's also how you determine which way the motor's going to spin, by rotating it that way. One of the most annoying things that we found setting up, especially Raptor 2 mass production, if you connect these the wrong way around and one of the motors spinning the wrong way, it adds another 5 to 10 minutes of disconnecting everything, putting it all back together, running the motor detection again, doing everything again, just because you got these two mixed up.
Right, yeah, so we're able to just automatically detect motor direction. So when you're just during config, you just spin them both in the forward direction, and it's done within probably 5 seconds, and you're ready to ride. So
wow. So not only have you sort of simplified that process, you've made it it's quicker as well. You can do the whole lot. I think you did a video of it the other day. I didn't time it, but how long would you say?
Maybe 3 seconds.
Yeah. So it's setting up motors now is so quick, so easy. I think it's fair to say anyone can do it.
Yeah.
And that's a huge thing for people that want to make electric skateboards at home, because like me, when I first started building, I knew nothing about electronics. I was never into remote control cars as a kid. I was more into skateboarding than the electronics. So I knew all about skateboards, but not about electronics. And it took me months and months to get my head around what was going on. And I think with a product like this, the end goal for us is to have it so that you really don't need to know fancy electrical engineering terminologies. You don't really need to know anything. You don't even need to know the specifications of your motor, because this can actually calculate the current that the motor can handle, the maximum current. And why is that a good idea? Is that going to stop people blowing motors up, do you think?
Yeah, so we've been working essentially on kind of what we did is we accrued a large data set of different motors and their maximum currents that they could handle, and based on the existing parameters that the motor controller is already detecting, we can estimate what is a safe maximum current for your motor. And is it going to be 100% the most accurate estimate ever? Maybe not, but it will be ballpark pretty close to correct. And because of that, we're going to save a lot of motor windings from melting, because we're finding that the estimates are hitting plus or minus just a few amps off of what the rated current is based on the parameters that we're looking at. And so it's going to help because it's going to protect your motor, because if your motor gets too much current through it too fast, it's going to heat up and it's going to melt. And a lot of motors don't come with thermistors inside them to make sure that they're not overheating. So you need to assign that parameter correctly, and it's not always something that the manufacturer provides, especially not with cheaper motors.
So correct me if I'm wrong, but the different ways that this can protect your motor compared to this, it's working out the maximum current that your motor can handle. But it's also got thermistors that are checking the temperature at the MOSFET and also inside the motor, if, of course, your motor is compatible with that, which some aren't. But, for instance, in the Raptor 2 motors, there's a little chip in there, basically, a little component that measures the temperature. There's also one on here. So how is that going to help protect the electronics?
Yeah, so the old FOCBOX had a thermistor on board as well, and most VESCs also, because it's really important to actively measure the temperature of the PCB and the MOSFETs, because if they get too hot, they will blow. The big difference that we've made here is that we've essentially moved the thermistor to be on the same piece of copper, the same physical piece of copper as the MOSFET. What that means is you're going to get much more thermal conductivity between the two. And so essentially, as your MOSFETs start heating up into a dangerous zone, it's going to detect that at a much faster time constant and be able to stop itself and throttle the motors before you ever get into a dangerous space that could damage your circuit board.
So it's about reaction time. You know, the more accurate the temperature measurement and the quicker it can react, that means you probably got a better chance of protecting the components, right?
Yeah, it's actually quite interesting. We did a lot of thermal testing on both of these boards to kind of compare their behavior. And we were seeing on the old FOCBOX, there was actually a bit of thermal overshoot where if you set your motor current super high to 80, 100 amps or so and really just punched it on that, there was a slight delay between when it was able to actually compensate, come in and cut the current. What didn't damage the FOCBOX, but there is possible that, you know, maybe some FETs out there could get damaged during that scenario. So who knows?
So the point is you just need a more accurate, quicker measurement to respond quicker. And the other interesting thing that I think you were surprised about is the performance of this. The amount of current that we were putting through this during our testing. Did that surprise you?
Yeah, definitely. I had, like I said, when I started this project, my focus was reducing costs. So my biggest thing, the biggest parameter that I was really focused on is called RDS on. And what that is when the MOSFET is switched on, right? Because essentially all a motor controller is a bunch of on and off switches, and it pulses them super quick in order to spin your motor, right? And so when the switch is turned fully on, the MOSFET still has some intrinsic internal resistance. And so as the current flows through it, that's what's generating all the heat. And so interestingly, the FETs that are used in the FOCBOX, the reason they're expensive is they're a great package for removing heat. So once the heat is generated, you can suck it out really quick, keep them cool. But internally, they actually still have a somewhat high RDS on for the price that they are. And so with the MOSFETs that I chose here, I was able to find some that had the same or lower internal resistance, but were just in a cheaper package that's much more common. And because of that, like more widely available, there's more competition, and that drives the price down. And so I was still concerned, obviously, because they don't have that same amazing thermal package, which is why I went for the single-sided design and opted to remove all the heat through the bottom of the PCB. But who knows how that's going to go, you know?
Yeah.
You could run some simulations, but I figured the best thing to do was just to put it together and test it. And the results have been pretty incredible, I think.
Yeah. What was the maximum current there?
Yeah, we were doing... Well, we were able to draw peak currents of around 100 to 110 amps.
Yeah.
And above that, we didn't really bother testing it, to be honest.
Yeah, I don't think people realize this at home, but that is a lot of power. You don't need that much power in your electric skateboard to make it throw you on your butt and accelerate faster than what you can handle. So that's really quite impressive. And considering the whole package is smaller as well. So normally or traditionally, as you build these kinds of circuits to handle more power, they get bigger. They have more MOSFETs on them. The cost goes up. But what's happened here is the price has come down. We haven't set the price yet, but it's cheaper for us to make it so the end price can be cheaper for our customers. The package is smaller, but it's going to be in higher performance. It's sort of hard to believe. Yeah,
it should be able to push about 130% of the current of the original FOCBOX. So it should be very competitive there.
And we've spoken a lot about hardware and whatnot, but this really is only half of the puzzle, right? There's software that you've worked on that goes with this. You touched on it briefly about the motor detection. You've done a lot of work there. What other things have you done with software to make this better for the end user?
Yeah, so a lot of what we focused on was, currently the state of the art, I guess you could say, is the VESC tool or the old BLDC tool. Both of those, they're amazing tools. The depth of configuration they offer is incredible. The problem is it's
pages and pages and
yeah. There's so many settings, and that's because these tools are designed to cover such a wide variety of applications, robotics, automation, a bunch of different stuff that you can use these for, and that's amazing. And we're still planning on supporting that tool and offering it for advanced users, so don't worry about that. But alongside that, we're gonna offer a simplified experience that's designed specifically for eSkate, where basically what it's going to do is it's going to remove all those complicated settings that really aren't going to have an impact on how you ride, and still bring to the surface all the settings you need to really customize how your board feels and the performance of it and the responsiveness of it. And that's just going to be the only things that you really need to pay attention to. And so you're going to get a much more simplified experience for your skateboard without losing any of that customizability.
Because some of the settings in the VESC tools and the BLDC tools of the past can actually break the hardware, right? You can actually put a setting in and it will destroy the hardware instantly. Can you do that with the new software? You've made it impossible to break, right?
Well, that's the goal.
Yeah.
I won't swear that because someone will prove me wrong, I'm sure. But
people are good at breaking stuff.
Sometimes. We're going to continually update it, obviously, as we go, and we're going to make sure that it's completely safe to use with your circuit board, and you no longer have to feel scared every time you click that right configuration button that you're going to blow up your motor driver board.
So basically, you've taken away all the stuff that's not needed, and the stuff that is left, you've made it so you can't really put the wrong settings in, and you've also made it so it's, I don't want to say artificial intelligence, but it's smart, right? It's able to answer questions that otherwise in the past, the user needed to put in the right information.
Yeah, we're trying to as much as we can, take the information that the motor driver can take in by itself and use that to get an idea of what your system is doing without you having to like wrestle with it too much, with just the very minimum user input, so that you don't have to be an expert in brushless motor control to configure your motor driver. Cool.
So lots of information here. If you had to say the top 3 things that you love about this, that you've realized has happened with this, what would you say they are?
Number 1 for me, because I'm always working with the board, is going to be the motor configuration. It's so fast and easy just in testing and working with it. Every time I'm swapping out, testing new motors, it's just one click, they're good to go, they're spinning, and I can go out and get a test done and save me hours of time.
I love that as well. For mass production, that is a game changer. I mean, 5 to 10 minutes less per board doesn't seem like much, but if you wanted to make 1,000 boards in a run or 2,000 boards, it's a lot of time saved. So what's number 2, your favorite?
Number 2 is I'm really happy with a lot of the cost saving features that I've been able to implement, and I think that's a big deal. Like, people don't have tons of spare cash lying around, and so if we can save some of these guys a little bit of money on their builds and enable them to, get something more, you can repurpose that money that you would have had to spend to get some nicer motors or get a bigger battery.
Yeah. So one of the things, unfortunately, that happens sometimes is when new technology or new innovations happen, it also pushes prices higher. We've seen that with other boards on the market based on the VESC project, where they had all this hype around them. They were meant to be amazing, but no one can afford them. Mm-hmm. So it's like unobtainable. No one gets it. With this, the cool thing is it's a step forward. It's an innovation. It's better performance. And I think the price is going to blow people away.
Yeah, that's the thing is, the reason sometimes that those new products come with such a high price is hardware development costs money. You know what? I have to get paid a bit. Everyone has to get paid a bit when they're making their new product. There's all kinds of new costs that the company has to take on. And luckily we can offset some of that with the cost savings that we're going to get in the hardware. And so that's going to make a big difference, I think.
I think the customers building skateboards is going to agree with that for sure. Okay. Third.
Final thing, probably, just increased power output. I'm so happy about this. The big thing too to say here is, you know what? Yeah, I can do 80 amps continuous and that's awesome. Most people don't need that, right? Even if you're still doing 40 amps, guess what that means? You're gonna have much higher efficiency. The reason that we can do 80 amps continuous is the motor driver is creating less heat. And what that means is you get to ride farther, your board's more efficient, and you're adding free range without any bigger of a battery.
Wow, and we haven't really talked about it, but one of my favorite things, because I designed it, is the case. This is actually what it's going to look like. This is actually a 3D printed one, so it's got a few funny lines and stuff on it that you might be able to see on the camera there. The final version of this is going to be full aluminium. Mm-hmm. So not only is the bottom a heat sink pulling the heat from the underside of the PCB, on the top side, it's actually going to be in contact with the MOSFETs as well. There'll be a little gap pad there, but then this top case is going to screw down and it's going to be pulling heat out of the top side and the bottom side. But it's about the mass of aluminium, I think, is the point.
Yeah, they'll help radiate some of the heat as well. It just depends what type of enclosure it's in, obviously.
But yeah, it's such a neat little package. And another really cool feature, it's not on this one, but you decided in the end to put USB-C on this thing.
Yeah, we've taken the full spectrum of USB connectors in our prototype revisions. We went mini, micro, and now we're on to C.
Wow. And what is the main benefit of that, do you reckon?
I think the biggest thing is just the robustness of the connector and just these ones here were weird and chintzy and we didn't like them. And and honestly, I don't know about anyone else, but my micro USB cables break constantly and I hate them. Mm-hmm. And I want to get rid of all of them. And so I'm excited to get my USB-C phone and this will be USB-C and we can all put micro USB cables behind us and be happier for it.
You don't have to second guess. It just goes in.
Yeah.
No matter which way you put it in. So that's going to be a cool little feature as well, I think. It's just nice to add some extra things when you can. If you're building something from scratch, you might as well try to make everything as best you can. I think that's a nice step forward. So anyway, I think that goes over most of the important information. Thanks for watching. I hope we gave you some answers and I hope you've got a better understanding of what it takes to develop hardware and software. And I mean, it's fun. We love it. We just want to make electric skateboarding technology better and better all the time so you can make awesome electric skateboards at home, or maybe buy a Raptor 2 as well, because eventually we're gonna this will be phased out and we will go to this in all Raptor 2s. That's really exciting. We're all about non-stop innovation at Inertian. We're not really happy with anything. We always see ways to make things better, and it's painful and annoying sometimes because development of products is hard and slow, and making changes takes a lot of time and resources. But at the end of the day, as long as we're pushing forward, trying to make the best hardware we can at affordable prices so people can make the most powerful electric skateboards money can buy in their own garage, we're happy. So high five to that, brother. See you later.